All right, here's a quick review of complex numbers because we're going to be using them to understand waves better. As you will recall, there's this thing called the imaginary number, and it is defined to be the square root of -1. All right? And you probably saw that somewhere earlier in life and wondered why in the world that was ever useful. You're going to find out in this class why it's useful if you haven't found a use for it earlier. And it turns out it's really, really handy. But anyway, just for now, just trust me that in the next lecture we're going to do some, in the next video we're going to do some cool stuff with complex numbers. Alright, so a complex number is a number that has a real and an imaginary part, right? So I can write it like some real number plus I times some other real number. This little tilde over the top, sometimes I write that over a variable just to remind me that it is a complex number and not a real number. Alright? You don't have to do that, that's something I do. Alright, so the real and imaginary parts of a number, that's just A and B. Alright, if I want to find the real part of a number, but the number doesn't happen to be written kind of like that, what can I do? Alright, well, first, the real part of this number is just A, right? The imaginary part is B. You might be tempted to say I times B, because that would make a heck of a lot of sense, right? And the imaginary part ought to be imaginary, right? But usually when a mathematician or a scientist says, what is the imaginary part of that number, they mean the real thing that you multiply by I, alright? So B would be the imaginary part, even though that seems a little screwy to me. Alright, now, there's this thing called the an Argon diagram, also known as the complex plane, and basically the idea is if I have any complex number, z is equal to 2 plus 3i, for example, I can represent that complex number as a point on a two-dimensional graphic, alright? So I'll let this axis be the real part and this part be the imaginary part. The real part is 2, so I come over 2. The imaginary part is 3, so I come up 1, 2, 3. And that point then represents that number. If I have some other number, z is equal to 6 minus 2i, then I'm going to come over 1, 2, 3, 4, 5, 6 real units, and then come down to 1, 2. Alright, so that point right there represents that complex number. So I can plot complex numbers on the complex plane, make an Argon diagram. Alright? Okay, now, let's talk about complex conjugates. The complex conjugate of a number, so I have some number here, a plus ib. To take the complex conjugate of a number, I simply just multiply all my i's by -1. So the complex conjugate of z is written as z with a little asterisk. That asterisk means complex conjugate, and that's just a minus ib, right? Let's say you had some complex number that was really complicated, all right? So maybe it's some complex number q times the cosine of some complex number m plus 3i divided by 2 plus 6i plus some complex number p. Alright? How would I take the complex conjugate of that? Alright, what you do is you just take the complex conjugate of everything in it. So I'm coming along, what's q? I don't know q, but whatever it is, let's take the complex conjugate. Then I've got the cosine of, I've got this complex number m. Let's take the complex conjugate of that. Then I have 3. 3 is a real number, so I take the complex number conjugate of it, and I just get 3, right? But I is imaginary, so I'm going to have minus 3i here, alright? Then down in the denominator, 2 is real. Then I've got 6i, that becomes minus 6i plus p. That's a complex number, so let's take the complex conjugate of it. So you just take the complex conjugate of something by taking the complex conjugate of all the stuff in it, and it turns out that that works. Alright. How do you find the magnitude of a complex number? What is the magnitude? The magnitude of a complex number is, if I plot a complex number in the complex plane, it's the distance of that number from the origin. Alright? How do you find the magnitude? Well, this length here is a, this one is b. We can use the Pythagorean theorem. R is equal to the square root of a squared plus b squared, right? But you can also use the complex conjugate, alright? Because watch what happens if I take some number z and multiply by its complex conjugate. Alright, z times its conjugate. That's a plus ib times a minus ib, right? If I write my complex number as a as a real part plus I times the imaginary part. Alright, my complex conjugate turns that plus into a minus. When I multiply this out, I'm going to get an a squared, a times minus ib, so that's going to be minus iab. Then I have ib times a, so that's plus iab. And then I get this times this. I get minus then I times I is minus 1, so that becomes a plus, and then I have b squared. All right, those cancel out, and this is just equal to a squared plus b squared. Hey, look at that. So if I take the square root of that, z times z complex conjugate, that's the square root of a squared plus b squared, but that's just Pythagorean's theorem. That's r. So the magnitude, right, usually we write the magnitude of something by putting these lines on either side of it. I can write the magnitude of a number as just the square root of a number times its complex conjugate. Groovy, huh? Or I can also write it as the square root of a squared plus b squared if I know the real and imaginary parts of that number z. Okay. Now, I can tell you a complex number by telling you the real part and the imaginary part, right? I can say z is equal to a plus ib, or I can say it's like, sometimes we write it like a vector, like a comma b, where this is a real part, this is the imaginary part, right? And I can display that on the complex plane, right? I come over some distance a, go up some distance b, and there's my point, all right? And if I tell you a and b, the real and imaginary parts, you know what the complex number is. But there's another way to represent complex numbers, and that's to give the magnitude of the number and the angle that this line makes relative to the real axis, all right? So if you have some number, z is equal to a plus ib, I can also tell you that number by telling you, instead of telling you the real and imaginary parts, I can tell you the magnitude of the number, and we call this the phase angle of that number, all right? The magnitude is just equal to, let's use Pythagorean's theorem, right? A squared plus b squared, square root of that. Or I can take z times, the square root of z times z complex conjugate, right? And that r is just, of course, the magnitude of z. How do I find the phase angle, theta? Well, I know that tangent of theta is equal to b over a. All right, so theta then is just the arctangent of b over a. Although you got to be careful, because if you take the arctangent of b over a, you can get this theta, or you can get that plus 180 degrees. So when you get this, plug this into your calculator and get the arctangent, then stop and say, is b positive, is a positive? Depending on whether a or b is positive, you may decide you need to actually add 180 degrees to what your calculator gives you to give you the right answer. All right? So there's a quick review of complex numbers.